Hello friends, welcome to Agar Modal YouTube channel. So this is Arun. So today we are going to see the some of the problems which was asked in IES and GATE examinations. So before that, the last video I made it little bit longer. The reason is that it is introduction part. You have to know all the details in the RCC structures. Then only we can move on to the next one. So kindly look at all the content that was talked in the last lecture, and I'll give the card for that introduction part in this video, and also I give the link to the description box. So today we'll see some of the problems which was asked in IES examinations and the GATE examinations. The first questions: an RC beam having a size of 250 mm into 350 mm overall is subjected to two point loads of equal magnitude placed at middle one third. The effective length of the beam is 3 meter. The beam is simply supported at the ends. The beam is reinforced with three bars of 16 mm diameter in the tension zone. Effective cover is 35 mm. Use M20 and Fe415. There are two cases. First one, determine the magnitude of point load at first flexural crack (FCR), neglecting steel and sulfate. Second case, determine the magnitude of the point load by considering the sulfate but neglecting the tensile zone. Okay, so here they are giving the depth and breadth of the beam, and they are giving load at two point loads, and the distance of the loads is 1 by third of each ends. The total length is 3 meter of the beam, and steel is provided at the tension zone. Three numbers of bars, each having 60 mm diameter bar, and the effective over 35 mm. Grade of concrete is M20 and steel is Fe415. So what they ask is the case one, they are asking the value of W with neglecting of the sulfate and the steel weight. Second case, they are including the sulfate but not considering the steel weight. Find the magnitude of W. So here, so first of all, in this question, so this is the pictorial diagram of the question what they are given. Three bars, each having 16 diameters at tension zone. So top is compression zone and bottom is tension zone. Then the breadth of the beam is 250 and depth of the beam is 350 mm, and the total distance is 3 meter, and there are two loads given. So both having 1 by third of total breadth, 1 by third of 3. So first of all, you have to find the using bending theory method. So we have to find m by I equal to sigma by y or f by y. So f is nothing but stress, cracking stress here, and y is the effective distance or centroid distance. M is nothing but moment, and I is moment of inertia. So where the moment of inertia can be calculated bd cube divided by 12, because it is a rectangular beam. So moment of inertia become bd cube divided by 12, and f here flexural cracks, so we are getting fcr. Y is nothing but the centroid value. So I equal to BD cube divided by 12. So we know the value of breadth is 250 and depth is 350. 250 into 350 cube divided by 12. So the value what we are getting is 893.3 into 10 power 6 mm power 4. And F is nothing but the flexural crack stress. So here the formula is zero point 0.7 root of FCK, which was we seen in the last video. So and Y, here it is a rectangular. Here y is the rectangular, so it is nothing but total depth by 2. So 350 by 2, which is equal to 175. Substituting all the values here, so we are getting the total moment as 15.97 kilonewton meter. Then the case 1, they are giving us two point loads, each having distance of 1 by third into 3. So each distance having 1 meter. So the maximum bending moment occur at the first flexural cracks. This was the case here at first flexural crack. Only two point load, neglecting all the self weights. So we have to find the maximum bending moment at this point. So here what they are given is at first flexural cracks you have to find the magnitude value. So the maximum bending moment occur at this point, first point, is nothing but the reaction at first left hand side into distance, so r into 1, which is equal to moment, so m equal to w. So why is that? W is nothing but the reactions for simultaneous beams, the reaction equal to total load divided by 2. So here the total load is 2W divided by 2. So the reaction each end we get is W. So the value is W kilonewton meter. So moment equal to W, then W equal to 15.98 kilonewton meter, because we already found that 15.98 kilonewton meter for moment. So considering that, so M equal to W, then W value is 15.98 kilonewton. Next, second case, considering the self weight of the beam. So here, not only the two point loads, along with that, we are considering the self weight. So for finding the self weight value, so we know that the density of the concrete into area into L is the formula for finding the self weight of the beam. So the density of the concrete is 25 kilonewton per meter cube, and area breadth into depth 250 mm breadth and 350 mm depth. So in terms of meter, 0.25 into 0.35, and length we consider as 1 meter. So with the calculation of this, the load what we are getting, the sulfate what we are getting is 2.187 kilonewton per meter. And already we seen in the previous case, so reaction equal to total load divided by 2. We can found either way in finding the moment equal to 0, and or else we can find the load value. So here the law of moment, the moment about B equal to 0, then the reaction at A into total distance 3 minus W into the remaining distance 2 meter minus W into 1 meter, and the value of self weight, so W into 3 into 3 by 2 equal to 0. Then after substituting all the values, we are getting RA equal to W plus 3.28. Then the, because of it is having the sulfate, it's in the form of UDL, the maximum bending moment occur at the center. So we have to find the moment at the center equal to, first of all, R into 1.5 3 by 2, W into 1 by 2, and the sulfate, so 3 W into 3 by 2 into 3 by 4. So after substituting this, we are getting moment equal to W plus 2.46. Then the equate them both the moment and the moment about A at the moment about center, we are getting the value of W as 13.52. So this is the case which was asked in the IES examination 2018. And the second question, on RCC beam having the size 300 mm into 600 mm overall is reinforced with 4 bars of 20 mm diameter in tension zone. The concrete grade is M20 and the steel grade is FE415. The effective cover is 40 mm. Here also there are two cases. Determine the maximum uncracked moment M suffix R, considering steel also. Second case, if an external moment is for 50 Newton meter is applied on the section, then what will be the cracking stress in concrete? So first of all, whatever they are given, so just draw the in the reinforcement drawing. So here, so breadth is 300 mm, depth is 600 mm, and the four bars at tension zone 20 mm diameter, and the transformer section, so there will be four bars, and for the bonding of the bars you have to provide some area of the concrete, so then only it gets good bonding. So the area of the concrete is M into AST. So first of all, find the modular ratio 280 by sigma 3 BC. So sigma 3 BC equal to 1 by 1 third of FCK. So substitute all the values. The value we got is 13.33. and area of the steel 4 bars at the tension zone at 20 m diameter. So 4 into by b for 20 square. So value we got is 1256.64 mm square. And the equivalent area of the concrete AC. So here AC we have to find is total area. So in that we are so finding AC total area. So in that we have to subtract these holes. So minus 4 times of by 4 d square, and addition of this bonding we are giving us m into ast. So b into d total area, so minus of area of the holes plus m into ast. So with the short form of this we will become bd plus m minus 1 ast. So substitute all the values, and finally we have to find the y bar. Why? Because we have to give the bending equations. So y bar equal to a1 y1 bar, a2 y2 bar, and a3 y3 bar. Here a1 is nothing but the normal concrete area portion. So a1 is nothing but normal area of the total beam, and a2 is nothing but the area of the hole. A2 is nothing but the area of the hole. A3 is nothing but the transformed section. So here A1 into Y1, so total area, so 200 into total area is nothing but 300 into 600, and y bar equal to 600 by 2, and a2 4 into pi by 4 d square, and y2 bar equal to the transform sections and the effective are given as 40 mm. Hence the y2 equal to directly we can give it as 40 mm, and the a3 is nothing but m into ast. We already seen that EAC equal to m into ast, and m ast we substitute that we'll get the value of a3, and y3 is same 40 mm. So substitute the 40 mm. So after substituting all the values, the value I obtain is y bar equal to 279.39, and we have to find the IXX because the formula is m by I equal to f by y. So we have to find all the values. So IXX equal to the first one total area Ig plus A1H square. So Ig PD cube divided by 12, and A 300 into 600. H is nothing but that y bar minus y1 bar. So y bar is nothing but total area 600 by 2, 300 minus y1 bar, the whole square. And ix2, because it's a small area, we can neglect the ig ig2, and we can calculate only a2 into h2 bar. So 4 bars pi by 4 d square, so substitute that one, and y bar minus y1 bar. So y bar 279.39, and y2 bar already given that 40 mm effective cover, so substitute that. So value 72.046 10 power 6, and ixs3. So this is also having the small area, so we can consider a3 into h3 bar. So a3 is nothing but m into ast, so 13.33 into ast 1256.64, and y3 bar minus y bar 279.36 minus 40 the whole square. So the value after adding all the values we got is 6.39364 into 10 power 9 mm power 4, and substitute that in the bending equation m by I equal to sigma by y. So we know that F equals nothing but cracking moment. So this is what given in the questions, that cracked and uncracking moments. So we have to find the F equal to FCR. So FCR equal to zero point 0.7 root of FCK, and I value we found that 6.364 into 10 power 9 divided by y bar 279.39. After substituting all the values, we got the value of moment is 71.3, and case 2. So they are given as additional moments of in the form of external moment 50 kilonewton meter. So substitute that one. So how much the effective stress held in that external load? So 50 divided by I 6.39364 and 10 power 9 into y bar 279.39. So the value of FCR we got is 2.195. So which is less than zero point 0.7 root of FCK. Hence it is safe. So what we are obtained is which is lesser than the what we are provided. So the section is safer, and the value of FST we have to find is m into FCD dash. So FC dash here, so we have to find the value of y bar minus f equal to y bar of that transform section divided by FCD dash. So here that FCD is nothing but where the transform section occurs, the portion stress is called that FCD dash. So we are found that with the help of this, they equate y bar minus FCD equal to y bar of transform section divided by FCD dash, and FCD dash 1.88 MPa, and the tension zone, the stress occur at the tension zone is nothing but M into FCD dash. So after substituting this, we getting the value of 25.0604, which is less than sigma st. And the third question, this is the major questions which was asked in both the GATE exam and IES exams, even for the TNPSC AE exam, combined engineering examinations also. This kind of questions more frequently asked. So question is, an RCC beam having a size of 250 into 500 mm effective is reinforced with 4 bars of 20 mm diameter in tension zone. Determine the depth of the limiting neutral axis. If the permissible strain in concrete in bending compression is 0.03, the effective cover is 40 mm, use M20 and Fe250. So this kind of questions most frequently asked in all type of questions. They are asking the effective depth. They are asking the depth for limiting neutral axis. So here they are giving us that bending compression is 0.003, and sigma st, we saw in the last class, sigma st, sorry, epsilon st equal to greater than equal to 0.02 plus fi divided by 1.15 into es, so or else 0.002 plus 0.87 fi by es. So we can say either ways. So we need to find the value of xu limit. So there is a equation xu limit equal to epsilon cb divided by epsilon cb plus epsilon st into effective depth. So the question itself given that epsilon cb equal to 0.003. So substitute the values, and the epsilon st we already know that 0.02 plus fi 250 divided by 1.15 into Young's modulus of steel 2 into 10 power of 5, and effective depth. So total depth is 500 mm. We can give that 500 itself, and the value of XU limit is 246.429. So these kind of questions you have to give more priority. So whenever you see the problems at, and that's it from today's video. So this is the most important questions which was asked in the previous question papers in the introduction part. And to subscribe the channels, and if you have any queries, you can contact me or you can put me in the comment box. So I'll answer you. And thank you.